Physics students, welcome to subtopic 11.2, which is power generation and transmission. And what I'm going to do in this first video is I'm going to talk very deeply about alternating current. Okay. Remember, we've already talked about direct current, and that's the current that results in a circuit when you simply connect wires to a battery. A battery provides direct current. The thing about alternating current, and we've talked about it actually quite a bit already, it involves Faraday's law. For example, when you have a rotating coil in a magnetic field, you know how the induced EMF goes from positive to negative and then causes the current to change direction. What we're going to do is we're going to talk about when that current changes direction periodically, which is what alternating current is when it comes to power generation and creating electricity for our homes and buildings and things like this. Okay, now up until now we got a changing flux from either a changing B field, changing area, or a changing theta. Okay, and we're not going to really consider again a delta N in this case because it's not really that practical. Now the question is, now what if any of these changes is regular or periodic, meaning it has a frequency and a period. Okay, so for example, in this case, I have a B field that's changing, okay, periodically, all right, and you can see that my AC current supply, I have an AC current supply. It's actually providing a current through those loops that's going back and forth, and then it creates an alternating magnetic field. Okay. Now, if the angle is changing, which is this is the one we're going to focus the most on. Okay. If the angle is changing, say this loop is made to rotate around an axis in a magnetic field. Okay, well, in this case, the external agent rotating the coil could be lots of things: burning oil, falling water, wind, power. In most applications of producing mass electricity, it comes down to boiling water, and when that water turns into steam, it turns these big turbines, which actually turns these coils. We'll talk more about that later. The point is that there is a constantly changing magnetic flux that is periodic. Therefore, there is a potential difference or an EMF in that wire that is constantly changing plus and minus, and that's actually periodic. And it turns out that the period and frequency of that changing EMF is the same as the actual physical rotation of that loop. Okay, and also the current is also constantly changing. Okay, so if you know the frequency with which a loop is rotating in a magnetic field, okay, that will produce a current that has that frequency, and it's called an alternating current because it's going back and forth at the exact same frequency that the loop is rotating in that field. Okay, all right. So the induced EMF changes polarity regularly. Therefore, so does the direction of the current. Okay, so here I have a current against time graph, and then I have a voltage against time graph. Both of these graphs are sinusoidal in nature. Okay, and again, the EMF is being induced because the angle theta is changing, and it's changing periodically. And remember Faraday's law. We said that the induced EMF, or epsilon, is negative n times b times a times the derivative of cosine of theta of t, okay? Because now we're considering this function theta of t. So we need to know the function, how the angle is changing as a function of time, okay? I just want to point out that the derivative of the cosine is the negative sign, such that you have the induced EMF is of this form right here. This is a very important equation that will be the foundation of everything we talk about in this video. Okay? Now, remember that for anything rotating at a constant angular velocity, if we deal with radians, we had this quantity angular velocity called omega, and that was theta over t, which was 2 pi f, because in this case 2 pi is the total radians around a circle, and t would be big T, which is actually the period. 1 over the period is the f frequency, and theta equals omega t. Okay, so in all of these cases we have an induced current. Okay, we have something that's rotating periodically. Okay, so Faraday's law then becomes this, which is what I had in the previous slide. Okay, it becomes, well, theta of t, theta as a function of t is really omega times t. Now, your rules of calculus. If you take the derivative of cosine omega t, what you have to do is you have to actually take the derivative of what's inside after you convert it to the negative sign, okay? The derivative of omega t is just omega. That's why we have this all-important omega term out here in front. So the induced EMF becomes omega times n times b times a times the sine of omega t, okay? And that's that original function, theta of t. Again, that is how theta varies with time. It's an exact function based on radians and the period and the total number of radians to map out a complete circle. Now, you can see that the maximum value of the induced EMF will be when the sine of omega t is 1, okay? That means that epsilon max is omega times n times b times a, okay? So that's pretty easy. It's called the peak voltage or the maximum voltage. So that the EMF induced in a rotating planar coil is, as a function of time, epsilon is a function of time, is epsilon max, because that's WNBA times the sine of omega t, where omega is 2 pi f, okay? And I just want to bring this kind of back to reality. Remember, this is the electrons and electrical energy oscillating back and forth with the same frequency as the voltage. Commonly, this frequency is 50 to 60 hertz in most countries, okay? And that goes back to, that's how fast, that's how many times per second, 50 to 60 times per second that coil is rotating in that magnetic field. That's pretty fast when you consider how big and massive that coil is, and it's in this gigantic, really strong magnetic field, okay? So there's all kinds of versions of this you can find online, really, really cool. I like these old-fashioned ones because it really beautifully maps that out. Look at this old-fashioned, they don't even use radians, they use degrees, right? That's pretty cool, okay? Okay, so what I'm going to do next is I'm going to walk you through 4 different kinds of graphs that it's crucial that you understand how these graphs are derived, and more importantly, you need to be able to reproduce these graphs in an exam situation. You need to be able to sketch what the graphs would look like. If you follow my words and follow my layout of my slides, you'll find that it takes some thinking, but it's actually not that difficult, okay? So I'm going to talk about graphs of the flux is a function of time, the induced EMF is a function of time, the current is a function of time, and then the power delivered is a function of time. And the first thing I want to say, they're all very, very similar because they're all sinusoidal curves, okay? Remember, a cosine function is a sinusoidal function. This term sinusoidal refers to anything that looks like a wave, like up and down, okay? And the frequency matches the frequency of the rotating coil in all cases, okay? All right. So I'm going to start, I'm going to base all of my discussion on a single example, okay? So imagine that you have a coil, okay? A planar single coil, so n equals 1, okay? And it's in a uniform magnetic field. Here going from the North Pole to the South Pole, of course. And the strength of that field is 0.4 Tesla. The area of the coil is 0.318 square meters. The coil is rotating 50 times per second, or in other words, the frequency is 50 hertz. And the resistance of the coil, the wire making it up, is 16 ohms, okay? First thing we got to do is determine the angular frequency of the loop's rotation. This is very easy, right? Because omega is 2 pi f, you've been given that f is 50. That's 100 pi radians per second, or if you don't like dealing with pi, that's 314 radians per second, or an angle of 314 radians per second, okay? So the general expression for the magnetic flux would then be, remember n is 1, we have phi of t equals b times a times the cosine of 100 pi t. That 100 pi t, that is my function theta of t. That's what I'm going to differentiate when I deal with the induced EMF, okay? Okay, so just to remind you, these are all the values that we just came up with, okay? Same idea, okay? First graph, we're going to talk about the graph of the flux against time. Now, remember that flux, we get a maximum flux when the plane is perpendicular to the B field, okay? But since it's going around, that flux, I'm not talking about the change in flux, I'm just talking about the flux, okay? That flux is itself periodic, and we can graph it, okay? All right, for this particular case, this is what phi of t against t looks like. So let's pick this apart and analyze it and see how we got these numbers. The most important numbers that we're interested in with all these graphs are the zeros of the function, where the maxima, local maxima and local minima occur, and of course the amplitude is also very important, okay? So we're starting off, we have phi of t is b times a times cosine 100 pi t, okay? Now, the zeros of phi of t are when the cosine is 0, right? Because the very function is cosine, okay? All right? Now, oops, okay? Or in other words, because it's a cosine function, the argument, the angle inside of these parentheses has to be pi over 2, 3 pi over 2, or 5 pi over 2, some multiple of pi over 2, right? Okay? So if you set 100 pi t equals pi over 2, for example, and solve for t, do the same thing when you set it 3 pi over t, 3 pi over 2, 5 pi over 2, okay? You get the following times, okay? 0.005 seconds, 0.15 seconds, and of course that corresponds exactly to this graph. Okay, here's the 0. Let me get my pen here. So here's the 0 right here, right? Here's another 0, okay? All right, pretty cool. Now the maxima or minima of phi of t are when the cosine is 1 or negative 1, okay? Now, to get those times, we set 100 pi t, which is the argument in these parentheses right there, either equal to 0, pi, 2 pi, because cosine is at a maximum at those radian values, okay? And we get 0 seconds, 0.01, 0.02, okay? That's here, 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 and so forth. Remember what's on my x-axis, the times are in milliseconds, okay? Okay, so I can then put in these values of time into my equation. I get phi of 0 equals 5.02 equals 5 of 0.04, and that is positive maximum flux, okay? And the maximum flux would be just B times A, and that's 0.127 Webers, okay? The negative maximum flux would be just negative that, and you can see that the graph corresponds very, very nicely to that. That's how that's how those maximum and minimum, or the amplitude of this wave, was obtained on this graph, okay? Whew, okay, you ready for the next one? Okay, here's the next one. We're going to talk about the graph of the induced EMF against time. It's going to get a little trickier, okay? Remember that the induced EMF is just the time rate of change, or the derivative of the change of the flux. Okay, therefore you can think of it as a slope graph in the previous graph, or it's the negative sign, of course, from calculus, right? Okay, all right. So here I am. I'm taking the derivative. I've done all this before. This is not mysterious to you, and if you're in calculus, you're very comfortable with this. Okay, all right. Now, I want you to note, and you will be asked the classic IB question, and that is, what is the effect of changing the frequency on these quantities? So I'm going to ask you, what's the effect of changing the frequency, or omega, on the induced EMF? Okay? Well, it turns out that if the frequency doubles, then of course omega doubles, because the frequency and omega are directly proportional, and because the induced EMF epsilon of t is proportional to omega, then that would mean that the induced EMF would also double, okay? Or halved, or whatever. They're going to ask you all kinds of questions like that. Now, similar argument to my previous slide. Zeros of the induced EMF are when the cosine are at a maximum, but the sine at a minimum. Because remember, this graph right here, this is a sine graph, not a cosine graph, okay? Again, I set the argument in the parentheses equal to 0, pi, 2 pi, etc., right? And I get that t is 0, 0.01, 0.02, which again corresponds to the graph, okay? The maxima or minima, okay, are just the opposite. It's when the cosine is equal to 0 and the sine is 1 or negative 1, and you know from your basic math that this is this right here. This argument in the parentheses is either pi over 2, 3 pi over 2, 5 pi over 2, right? Because I'm dealing with a cosine argument, okay? Right? And I get 0.005, 0.015, and just like before, I can find the positive induced EMF and the negative induced EMF. And the reality is, when we're solving circuits and dealing with things like this, we only really care about the magnitude. But in this case, the magnitude is about 40 volts, 39.9 volts. That's where this value, this amplitude of that wave comes from. It's from this calculation, okay? All right, let's do another one. Let's do the current against time. Number 3, the third super important graph that you're responsible for. Okay, we don't have to take any more derivatives, okay? We're not dealing with second derivatives or whatever. Now we're going to use Ohm's law. So this is pretty easy. I mean, you've done Ohm's law before. It's a piece of cake for you guys. Only the difference is that I'm using Ohm's law with a varying current and a varying V. I and V are not common, which is the whole point of alternating current, okay? So now Ohm's law becomes I of t equals V of t over R, okay? All right, and that's going to be the maximum voltage times sine omega t, as we saw before, over R. But this quantity, V max or epsilon max over R, that's the maximum current. So I can also write it I max times sine omega t, okay? Now, again, what's the effect of changing omega on the current? Well, just as before, if omega doubles, then I doubles, because I of t is directly proportional to omega, which in turn is directly proportional to the frequency, okay? All right, so once again, here we go. The zeros correspond to those exactly of the previous argument of the induced EMF, right? We don't even have to do those calculations anymore, right? And why is that? Because I of t is just exactly V of t, but only divided by a constant, or multiplied by 1 over R, which is a constant, okay? So we just get, all it's going to happen is that we're going to have different values on the y-axis. That's all it is, okay? So the maximum and minima correspond to those of epsilon of t, so forth, okay? Everything's the same, okay? I want you to notice that the peak current here is 2.49 amps, okay? Let me show you how that is. Well, that's just I max, and I max is V max or epsilon max over R, and that's omega BA over R, which is just 2.5 amps, positive and negative, okay? So this one's pretty simple, right? Just remember that I of t is not mysterious. It's just your epsilon of t multiplied by a constant, and that constant is 1 over R. And that comes from Ohm's law. That is Ohm's law, okay? All right, the last one, and that's the power, because after all, don't we care about the power? That's ultimately why we're doing all of this, to deliver power, right? Which is just energy per unit time. So we better look at this graph. Now, the first difference you notice about this graph from the other ones, it's sinusoidal in nature, but it doesn't go negative. And that's because power can't be negative. We're delivering energy per unit time. There's no such thing as negative power or negative energy or that sort of thing, okay? Now, from our previous studies of circuits, we had a couple of flavors. We had a couple of different versions for power. Remember, we said P equals VI, P equals V squared over R, etc. Okay. So in this case, I'm just going to consider the simplest version, and that's P equals VI. Okay. But now I have, since V is a function of time varies, I is a function of t and it varies, P is going to be a function of t. It's going to be the multiplication multiplying two different time varying functions together, which I know you can do. This is easy. This is not difficult math, right? You end up with V max times I max, but now we have a sine squared function. And you know from mathematics that when you square the sine, what happens is it bunches up, right? Okay, so I have epsilon max times I max times sine squared of omega t, okay? Now things are different. When you get asked that question, when the frequency changes, for example, if the frequency doubles, what happens to the power, okay? Well, if frequency doubles, omega will double, because omega is just 2 pi f, right? However, there's an omega, there's going to be an omega squared in here because both Emax and Imax both have omegas in them. So therefore, P is increased by 4 times, okay? Now, after this, the math is fairly easy. So the maximum power is going to be the maximum voltage times the maximum current, which we found in the previous slides. That's 39.9 and 2.49. It's 99.4. That is where we get this value, right? That's where we get the amplitude of this sine squared wave, okay? Now, what if we think about it in other terms, right? What about V squared over R, for example? Well, that's this right here, right? It's all the same thing, okay? We get all the same thing depending on which flavor of power that we use from before when we studied circuits previously, okay? So again, you're responsible for all 4 of these graphs. You may not have to derive them mathematically in such detail, but you need to have a pretty deep understanding of how they're related and be able to reproduce them in an exam situation, which can be tricky, but as long as you keep your head and keep calm and keep cool and convince yourself that you know how to do it because you now know how to do it from this video, things should go very smoothly for you.